Welcome to the Using Hardware in the Loop, HIL for Rapid Simulation, with AMD Adaptive SoCs Quick Take video. In this video, we'll walk through starting with what is VSS, Introduction to HIL, its workflow and setup, and conclude with a demo presentation with an example design. Before discussing hardware in the loop, it's helpful to first understand the concept of the AMD Vitis subsystem, or VSS. In the Vitis development environment, heterogeneous systems are built by combining different types of compute kernels. These can include AI engine kernels, HLS kernels, and RTL kernels running in the programmable logic. Together, these components form a complete hardware-accelerated design. To integrate these components, Vitis uses a subsystem linking flow. During this process, the linker, invoked through the v++ command, connects the different kernels and generates a .vss file. This file represents the entire subsystem and defines how the different elements of the design work together. This subsystem abstraction makes it easier for developers to manage and build complex heterogeneous applications while maintaining a clear structure for integration and deployment. With the subsystem created, the design can then move toward further verification and validation workflows within the Vitis environment. This is where Hardware in the Loop, or HIL, provides an alternative approach. Hardware in the Loop verification enables designs to run directly on real hardware, allowing much faster validation compared to traditional simulation. By executing the design on an FPGA platform, developers can observe behavior under realistic operating conditions. In this flow, heterogeneous designs containing any combination of AI engine, HLS, or HDL components are first compiled into a Vitis subsystem. This subsystem is then used to generate a bootable SD card image for a development board, allowing the board to operate as a HIL server. On the host system, a MATLAB API or Python API can be used to send test data to the board and retrieve results through an Ethernet connection. The hardware processes the incoming data in real time, and the results are returned to the host system for analysis and verification. By combining real hardware execution with host-based analysis tools, Hardware in the Loop enables faster and more realistic verification of heterogeneous designs. To better understand how this works in practice, let's look at the overall workflow of Hardware in the Loop. The workflow consists of two primary components, the HIL server and the HIL host. The first step is to set up the AMD Vitis environment. This ensures that all the required tools, libraries, and dependencies are available before starting the process. Once the environment is ready, the next step is to generate a Vitis subsystem for the design. This subsystem forms the foundation for the HIL workflow and allows the design to be compiled and executed in the hardware validation setup. The generated subsystem is then used to build a bootable SD card image using the HIL_GIN command. This command requires several key arguments. The VSS argument specifies the directory containing the VSS build. It's important to note that this refers to the directory itself, not the .vss file. The P argument provides the path to the base hardware platform file, typically a .xpfm file. The SDK argument specifies the path to the SDK used for the build environment. The rootfs argument points to the pre-built Linux kernel and root file system for the target hardware platform. Optionally, a CFG option can be used to reference a configuration file. This simplifies the workflow by storing commonly used paths and settings. Instead of specifying all command line options each time, a configuration file can be used to capture the required settings in a single place. This file stores information such as the VSS directory, platform file, SDK location, and root file system. If a configuration file is not provided, the tool automatically generates one during the first run using the command line parameters. Once created, the same configuration file can be reused in future runs by referencing it with the CFG option. When the HIL_GIN command completes, it generates a structured output directory containing the files required to run the HIL server. Two important files are produced during this step. The first is HIL_interface_spec.json, which defines the communication interface and port configuration of the design. This file is used by the host application to understand how data should be sent to and received from the hardware. The second is SD_card.img, which contains the bootable image that will be written to an SD card and used to boot the development board. Additional directories such as SD_card and work are also generated to organize supporting files and build outputs. Once the SD card image is prepared, the development board can be configured to run the HIL server. The board is first set to boot from the SD card using the appropriate boot mode settings. After inserting the SD card, a serial connection is established between the host system and the board using a terminal application such as PuTTY. After the system boots, the default login credentials can be used to access the board. From there, switching to the root user allows administrative access for configuring the environment. Next, the board is connected to the host system through an Ethernet link, either directly or through a local network. If required, network settings such as the IP address can be configured. Once the connection is established, navigating to the SD card directory and launching the HIL_server.sh script starts the HIL server on the board. On the host side, MATLAB or Python can be used to interact with the hardware through the HIL API. The first step is to import the HIL module, which provides access to the functions needed for communication with the hardware system. Next, a HIL object is created. This object is generated as part of the build process and references the interface specification file created earlier. It acts as the bridge between the host software environment and the hardware design running on the board. After creating the object, a connection is established to the development board using its IP address and port number. This step links the host application with the running HIL server. Once the connection is established, developers can explore the design's interfaces. Optional API functions such as getInputSpec and getOutputSpec allow users to inspect the available input and output ports. These functions help verify how data flows into and out of the hardware design and ensure the host application is configured correctly. After reviewing the interface information, the next step is to ensure that the data types used in the host application match the hardware design. This is particularly important when HDL components are present at the IP boundaries. The host application must interpret the signals correctly, and the selected data types must align with the bit widths defined by the hardware ports. Configuring these data types ensures that communication between the host and the hardware remains consistent. Performance parameters can also be configured to optimize the hardware-in-the-loop setup. Using the API, developers can adjust settings such as frame size and timeout values. Frame size determines how much data is transmitted in each batch, while timeout values define how long the system waits for responses from the hardware. Together, these parameters influence the overall throughput and responsiveness of the HIL workflow. Once everything is configured, the hardware-in-the-loop process can be executed from the host application. The HIL object is first initialized to prepare the connection and ensure the hardware is ready to receive data. After initialization, the host application can send input data to the hardware and trigger execution. As the design processes the input data, the resulting outputs are returned to the host system. However, it's important to note that the amount of output data returned during each execution may vary. The run method in the HIL API can produce different amounts of data depending on how the hardware processes the input stream. In some cases, multiple frames of data may be returned. In others, fewer frames, or occasionally no data, may be available during a single call. To handle this variability effectively, buffering techniques are often used on the host side. Buffering ensures that all returned data is properly captured and organized before it is analyzed or passed to the next stage of processing. By combining real hardware execution with flexible host-side analysis, hardware-in-the-loop provides an efficient and scalable method for validating complex heterogeneous designs. Now I will demonstrate how to use hardware in the loop to verify an AI engine design. Begin by setting up AMD Vitis 2025.1 using this command. To follow along with this video, clone the Vitis Tutorials GitHub repository at github.com/xylink/Vitis Tutorials. Navigate to the Bytonic sorting directory in the AIE Design Tutorials folder. I will use the Bytonic FP16 design for this demonstration. This demonstration assumes that your design's AIE, HLS, and HDL kernels have already been compiled. Refer to UG 1701 for specific details on compiling kernels. This example Bytonic sorting AIE design can be compiled simply using makelibadf.a. Next, we need to generate a Vitis subsystem for this design. This process begins by creating a VSS configuration file. This configuration will be very basic since this VSS will only consist of a single AIE kernel. Save this config file and run the v++ command with mode set to VSS. Use the part argument to point to your specific device. The config argument should point to the VSS config file created earlier. Refer to UG 1701 for more details on generating a VSS. This VSS can now be used to build a HIL server SD card image. Use the HILgen command with the following required arguments. -VSS with the path to your VSS build directory. Note that this is not a path directly to the .vss file itself, rather the directory containing it. -P with path to the desired base hardware platform file. This will be a .xpfm file. -SDK containing path to SDK. -rootfs containing path to the pre-built Linux kernel and root file system for your hardware. Optionally, use -cfg to point to a pre-made HIL _gen config file if needed. Otherwise, a configuration file will be automatically generated from the CLI options. Two key files are generated by this command. HIL_interface_spec.json will be used by our MATLAB host application to define the design's ports. SD_card.image will be flashed onto an SD card for use with our dev board. Use a tool like Raspberry Pi Imager to flash this SD card image to an SD card. Set up your development board to boot from the SD card. I will set my VCK 190's boot mode switch, SW1, to 0001. Use a terminal emulator to connect to the development board over serial. On the VCK 190, the processing system's UART is connected to the second serial port associated with the FTDI controller. If you are on Linux and have no other TTY USB devices connected, this serial port will be TTY USB1. Use the default username PetaLinux to log in and set up a password. Switch to the root user and set up an Ethernet connection to the host PC, either directly or over a local network. Use ifconfig to set a static IP address if needed. Navigate to the /run/media/mmcblock 0p1 directory. Run the HIL_server.sh script in this directory. Now, switch to the host PC and create a HIL host MATLAB script. For this example, I ported over the x86 sim section of the gen.vectors.m script in the Bytonic_fpkey 16 directory. Utilize the MATLAB HIL API to interface with the development board. Create an HIL object that references the interface spec JSON file auto-generated by the HIL_gen command from before. Also reference the specific IP address of your board. Note the use of the port number 8888. This is the fixed port number that HIL server listens on, and it cannot be changed. AMD devices may use data types that are unsupported by MATLAB. AMD provides the V-Array library to convert and cast between MATLAB and AMD device data types. Refer to Chapter 6 of UG 1701 for more information on how to use V-Array. Use MATLAB to generate stimulus for the design. For Bytonic sorting, I will generate a column vector of random floating point numbers. I will then use MATLAB's sort function on this random vector to create a golden reference column vector. I will create a matrix of these column vectors, where the number of columns is the number of desired test trials. Use the runMember function of the HIL object to send data to the HIL server running on the development board. This function returns data from the HIL server over the Ethernet connection set up earlier. Note that all data sent and received must be a V-Array data type. This run function method can return varying amounts of data per call, sometimes no data at all. If multiple outputs need to be synchronized, a FIFO should be coded in the host application. Verify the data returned from the HIL server. I will calculate the error between the golden reference matrix and a matrix consisting of data returned from the HIL server. This algorithm is now successfully verified on hardware. Let's wrap up with the key takeaways. First, Vitis subsystems make it possible to integrate heterogeneous components, AI engines, HLS and RTL kernels, into a single unified design. Second, traditional simulation and emulation often struggle with large heterogeneous systems, and for algorithms that require acquisition or convergence, the amount of data needed for verification is substantial. In those cases, simulation simply isn't a viable option to get results in a reasonable time. Third, hardware in the loop accelerates verification by running designs directly on real hardware, giving you speed and accuracy together. Finally, the HIL APIs and the server host architecture allow developers to send test data, collect results, and analyze system behavior efficiently. This makes the entire verification workflow smoother and more scalable. Thanks for watching this video.